unprovoked, unforeseen cut-off of the first video. It was my intention to complete the conceptual framework in one video only, but my camera shut down at 1 hour mark. So as I was talking about, so let me just start this question again. It's an exam caliber question that talks about electrolysis of aluminium in a solution of cryolite. So cryolite consists of alumina and cryolite. So it's a solution of alumina in a molten cryolite. Solution of alumina. So solution. So it's molten. So it's solution, not a molten alumina in molten cryolite. So cryolite's molten, but alumina is acquiesced. So the first question was, why do you think it's too expensive to extract aluminium by electrolysis of molten aluminium? Because of its melting point. So it's produced in aqueous form, so that it's easier to ionize the ions, and then it's added to a molten cryolite. Now that's the first part. The first part is its melting point. So it's being lowered by adding cryolite, which is more of an ore like bauxite. More of an ore, like bauxite. So why do you think it's too expensive? So it's expensive because of its melting point, and it's also expensive because alumina on its own shall only produce 2 atoms of aluminium per mole. So two moles of aluminium per mole of alumina. Here, with a little bit of impurity, you can get 1.5 times the yield than alumina. So that's why this ore is very, very useful. So in terms of molar proportionation. The second question was, please write down the equation for production of aluminium metal and oxygen gas. So I've done that here. We did that in the previous video. The anode requires frequent replacement, and as I just spoke about it, it's because the oxygen being released at the anode continues to eat into the graphite by producing carbon dioxide. So graphite, which is carbon, allotrope, continues to get consumed by the oxygen getting released at anode, and it continues to be eaten into by the oxygen being released at anode, and so it has to be replaced at a certain frequency. So periodic replacement is necessary because carbon dioxide is produced as a result of it. So now, if 100 amps, now the question number D is a current of 100 amps produce 2.7 grams of aluminium 5 minutes. Calculate the number of coulombs required to deposit 1 mole. 1 mole. So we can see this is a tenth of a mole. This is a tenth of a mole. 2.7 grams of aluminium is a tenth of a mole of aluminium. So 1 mole of aluminium would be 10 times more of that, and it should require around about 10 times more charge. But we need to verify that. We'll verify it now, and it would be using the same formula. Mass equals Q over F times AR over Z. Now this formula is very, very handy, comes in handy every single time. So for 1 mole it will be 27 grams, and then we need to find a coulomb. We've got Faraday constant 96,500 coulombs per mole times 27 grams per mole divided by 3. So we'll rearrange it for Q. So that will be 27 grams times 3 times 96,500 coulombs per mole. I'm sorry, but you have to mention coulombs, the units every single time. And that'll be 27 grams per mole. And it cancels out. I should have cancelled it there, but there we go. So it'll be coulombs. Now, what was the amount used in amperes? It was used, so the now we need to check whether it's 10 times more. So this is the amount of current or charge that will be used to produce 1 mole of aluminium. Now industrially it'll be quite different because of equipment malfunction or equipment systematic errors, but in so is it really 10 times more than that for 0.1 mole of aluminium? That'll be 100 amps times 5 times 60. So it's 30,000 coulombs. So this is round about 300,000. So yeah, it is round about 10 times more. Round about 10 times more. So this was 30,000 coulombs, 30 kilocoulombs, and this is 289,500 coulombs, which is round about 300,000 coulombs. So it is 10 times more, yes. So the ratio does exist. But I just couldn't write 300,000 coulombs because I wouldn't get any mark for it. I have to show the whole calculational procedure to get to this answer, and then I can then reverse check in my mind that yes, it is 10 times more, so my answer must be correct. Now it says use your answer in D2 to show that the charge or the oxidation number on the aluminium ion is 3 positive. Again, you would use this favorite equation of mine. That's mass deposited equals IT over F times atomic mass divided by the oxidation number. Brilliant equation. Serves right every single time and saves you a lot of time and effort. Now, this has been a very thrilling adventure pertaining to electrochemistry. I think we've covered a lot in this 1.25 hours. So now I'll be taking you through all of these exam questions in Ramsden and Sykes books. That will prepare you thoroughly with rigor and virility to tackle any sort of advanced electrochemical calculational question in your GCSE or AS or A level. The only thing I haven't touched yet is the Electrochemical Series, which is closely linked to the reactivity series, which is sodium, potassium, calcium, magnesium, iron, lead, hydrogen, copper. So the Electrochemical Series will come later, which is simple. It's just a salt bridge, and you have to subtract the voltage of the right hand side from the left hand side, and that's pretty much it. But these type of calculations are the ones that have been not been used, that have not been So I'll now try to tackle all of these questions one by one, and I'll take it from here.